The study of the Lorentz group in 4 dimensions is very much tied to SU2. So it pays if you want to have a deep understanding of the symmetries of space-time in 4 dimensions. It pays to be as familiar as you can with SU2. And furthermore, even the higher, the larger groups, SUN and so on, in fact, are related to these SU2 representations, right? So once you understand it, it's easier to go from there to understand the larger groups. As I've said before, especially even in quantum mechanics itself, it's much of the analysis in quantum systems are related to their symmetries. And so it is extremely important to get yourself familiar. The deeper you go, the more important you will discover these discussions of symmetries. So for example, maybe I would just say very briefly, when you do relativistic quantum field theory, you will discover that there are 2 copies of these SU2 algebra. What you will discover from there is that from there you will discover the notion of left-handed and right-handed spin-half systems, right? So we call them wild spinners, but they are basically the relativistic generalization of what we just did for SU2, right? So the reason why there are 2 pairs is because now you have to incorporate not just the rotations that we are talking about here. The SU2 we're talking about is the analog of rotations, but applied to spin-half systems. But when you are in relativistic, when you're doing relativistic quantum field theory, you not only have to worry about or think about rotations, you also have to think about Lorentz boosts. So when you incorporate the whole Lorentz group, boosts and rotations, you will discover you need more symmetry generators, right? But what you discover is that you can break it down. You can break down the generators in such a way that basically gives you 2 copies of SU2. So that's an example of why it is important. It shows up in many other contexts. So like I said already, knowing SU2, knowing rotations, is going to be very important. The more physics, the more fundamental physics you need to do. Okay, so today I'd like to begin talking about some applications of what we've been talking about, right? So what we've been doing so far is to understand more deeply how to apply the notion of rotations to quantum systems. But now let's actually work out some examples. And of course, one of the most important examples is that of the hydrogen-like system. And let's write down what that looks like. Okay. Just find my notes. So for the applied hydrogen-like atom, what we have is basically a core We have a core of we have a central core with Z protons and a total number of protons and a total number of protons and neutrons, right? So hydrogen-like atoms. Okay. So what we will have, for simplicity right now, is that we will have a central core of Z protons and A minus Z neutrons. Okay, so this is my nucleus. And out here, you have your electron. Okay? And mainly we're interested in what's the energy level that these electrons can take, right? Of course, we also can solve for the wave functions, but what we can probe most readily are the energy levels, and in fact, not the energy levels directly, but actually the differences in energy levels. That's the thing that we can probe most easily. And in fact, this was the beginning of quantum mechanics, where we looked at these spectral lines. I think I had a brief discussion of this at the very beginning of the semester. And the attempt to understand why these jumps in energy levels gave you discrete lines, discrete spectroscopic lines when you looked at the colors of the light coming in, was what led us to ultimately discover quantum mechanics, right? So this is kind of the key problem to check our understanding of quantum mechanics. Right? If you can't describe this, then you don't really understand quantum mechanics. So, but now we actually do know how to do this, because we know the formalism of quantum mechanics. And so the key point is, what is the Hamiltonian? Right? So in the non-relativistic context, the key point is to usually write down the kinetic energy plus potential energy. Right, so at some point I should also give you guys a brief review of Hamiltonian dynamics, in case people have not done this very much. Yesterday I asked my quantum field theory class how many people know that time translation symmetry implies energy conservation, and space translation symmetry implies momentum conservation, and not everybody knew that. So probably I have to review some of these stuff. So in the context of the hydrogen atom, kinetic energy is just p squared over 2m. In fact, this part we have talked about quite a bit. This is what gives you the Laplacian in the position representation. For the potential energy, because it's an attractive potential, so this is going to be negative, right? And because there are Z protons in the core, we would usually write down Z E squared over R, right? So this is the potential energy. So if you do relativistic quantum field theory, or relativistic quantum mechanics for that matter, why I keep saying quantum field theory is because that's the more fundamental framework. You can derive corrections to this, right? So So let me just say from the outset, there are actually infinite number of relativistic corrections. Maybe next semester we will talk about how to include them in a perturbative way, right? So if you are interested in learning how to deal with them, make sure you take the next semester where we are going to do perturbation theory. So for now, I'm going to be simplistic and simply regard the nucleus as an infinitely heavy central body. And so the mass of this guy will simply be the mass of the electron. But strictly speaking, I will give you a homework problem where you will work out how to work this problem out, incorporating the mass of the central nucleus, right? So what's going to happen is that, again, if you know your classical mechanics, the two-body problem, you will know that actually what shows up eventually in the mass over here is the reduced mass. It's called the reduced mass, which is basically a combination of the electron mass and the mass of the nucleus. So what you discover is that as the nucleus gets heavier and heavier, the approximation that this mass is the electron mass gets better and better. For the hydrogen atom, you would just have Z equals to 1, and A is also equals to 1. And there you will find that the fractional correction, whenever you see the mass appearing in your formulas, you will need to correct the whatever answer you get. If you had electron mass in your answer, the actual answer will be corrected by order of 0.1%, because the mass of the proton is roughly 2,000 times more, 2,000 times off the electron mass, right? But anyway, for now, we're going to focus on the electron, and I'm going to assume that we can treat the central nucleus as infinitely heavy.
Excuse me.
Yeah.
Is the mass of the electron here is constant, or it depends on the velocity of the electron?
It's a constant, yeah. So maybe you're thinking about relativity, right? So later on, when you include relativistic corrections, then there'll be higher powers of momentum that comes in. But mass is always a constant. So the electron mass is roughly, in terms of EV, 0.511 MeV, right? In units where C is 1. So MC squared. So if you want, better put in a C squared. Yeah. My H bar is 1, but let me not confuse you further. So this is the electron mass, and the proton mass. The proton mass is this I don't know up to I know this up to 3 decimal places, but this is roughly 1 GeV or C squared. Right, so you can see it's about 2,000 times. Yeah. So when I talk about masses, I always mean the constant, the rest mass, basically. Yeah. Okay. So how do you do this? So now that you know the spherical harmonics, you can recognize that this guy is rotationally invariant, right? So H, you notice, is rotationally invariant. How do you see that? Well, this guy is rotationally invariant. So the easiest way is, of course, to write it down in the position representation. And when you rotate P, so remember what will happen is that when you do R dagger of say P dr, what is this guy? What you will discover is that let's say you apply it on a momentum eigenstate, then this will rotate the k, and when you apply it to p to this guy, you will basically discover that this is r applied to p applied to k, yeah, that's right, to k. Okay, and so therefore, you will discover that basically you can erase the eigencat and realize that this is an operator statement. Sandwiching p between the rotation operators change the basis and basically amounts to rotating the components of the operator, momentum operator. Okay, and likewise for the position operator, which shows up in R. Okay. So again, P and X are operators, but R hat are the components of the rotation matrix. So they're not operators, but they will rotate the components of the P and X. So so when you sandwich P squared between the rotation operators, because it's P squared, you will end up with P dotted into itself, because rotation is, the rotation matrices are orthogonal. So this is just the operator statement that you're familiar with from vector calculus, right? If this were just vectors, then you know that P dot P is rotationally invariant. That's how we started with the rotation group. But because they're now operators, we have to use this statement instead. So likewise, if you are looking at things like x squared, it is also preserved by rotation. Right? Again, it's rotational invariant. But R is just basically the reciprocal of 1 over the square root of x squared. So this is preserved. R is also preserved. Right? That's how we think about it. So therefore, H. So these two statements together imply that d dagger H, d, for any rotation is in fact H. Okay, and that tells you that I've said this before, that we expect that we can use J squared, the square of the generators of sum of the squares of the generators of rotation, and J3 and H are compatible observables. And this is why we're going to try to diagonalize, simultaneously diagonalize these operators. So what that means basically is that in the position representation, if you're interested in the energy eigenstate, what we want, where's my eraser? So what we want is to diagonalize the Hamiltonian, and what that means is that in the position representation, we want to solve for these guys. And what it will turn out is that for the hydrogen atom, it's going to depend on a number n, and we are going to solve for En. But because it's rotationally invariant, we also know that these guys should be simultaneous eigenstates of J squared and J3. So En should also be simultaneous eigenstates of L and M. Simultaneous eigenstates involving L and M. Okay? And in fact, what we'll discover is that the hydrogen atom without any spin, yeah, so we haven't included spin. In fact, is completely degenerate in L and M, right? So this is something that is a little bit of a mystery, but next semester, because I think we might not have enough time to talk about this semester, why is degenerate. But next semester, we'll discover that the hydrogen atom actually has more symmetry than just rotations. In fact, right now we're talking about three-dimensional rotations, right? But what we'll discover next semester is that in this particular system has actually four-dimensional rotations symmetry. And that four-dimensional rotational symmetry, in fact, is what's going to give us this additional degeneracy. Okay. Remember, the key point that you should remember is that symmetry implies degeneracy. Right? We did a discussion of this for rotations as well. If you have rotational symmetry, in general, you would expect that all the m values have the same eigenenergy state. And if the Hamiltonian commutes with the generator of rotations. But now we discover by explicit calculation that En will turn out to also be independent of L, right? So for now it's going to be a mystery, but if you stick around until next semester, we will discover why. Okay. So because this is the case, as you can guess, what we're going to end up doing is that this will be split up into YLMs. This, we're not talking about spin yet. So these will be just spherical harmonics times a radial wave function. Okay. That's what's going to happen. So, like I said before, we already expect that in general, the E is not going to depend on M. So the radial mode function itself, we will expect that it will not depend on M, but it will also turn out not to depend on L. But let's write down first, what does this look like? In fact, also for simplicity, I'm going to write down the minus E here. So En for now is minus, let me call it E bar N. Okay, it's equals to E bar N. I just want to pull out a minus sign. As you guys probably already know, the lowest energy state is negative 13.6 eV, right? So I just want to pull out the minus sign. Okay, so let's in fact write it down. So if you remember, what we will have from here in position space, if you remember the P squared is minus Laplacian in position space, that would allow you to write down quite quickly that this is just minus 1 over 2 ME, okay? And then this is Laplacian on the wave function. So this is going to be the usual wave function. And then this is going to be minus ZE squared over R times psi of x, and that's going to be minus E bar n of psi of x. Okay? And so you can work out now what it looks like in position in this decomposition. And so if you remember that the Laplacian on the sphere acting on YLM, so remember that this guy is a radial piece plus L squared over 2 over R squared. That's a minus sign. And the L squared is just basically the orbital angular momentum, which is actually just minus Laplacian on the sphere acting on YLM. This is L times L plus 1. Let me just write this down. This is actually equals to L squared YLM. This will be L times L plus 1 times YLM, because YLM is the eigenfunction of the Laplacian on the sphere. Then you will discover that this is actually separable. And what you will discover is that your wave function equation reduces to just a ordinary differential equation. Okay, so I'll just go ahead and write down what it looks like. R double prime of little r over 2me minus r prime of little r over me r, and then plus E bar plus L times L plus 1 over 2me r squared minus ZE squared over R times R little r equals to 0. Okay? So again, you use the Laplacian will act with R derivatives on psi, which will act on R, and then there will be an additional term that involves the Laplacian on the sphere acting on psi, but Laplacian on the sphere will now act on YLM, and that's what gives you this L times L plus 1 term. Okay? And once you're done with that, then you can basically cancel out the YLM on both sides and rearrange your equation, rearrange your Schrodinger equation into just a single ordinary differential equation for R. Okay, and what we'll see is that the energy levels are going to be determined by demanding that R, capital R, behaves well at infinity. Okay. So Weinberg has a more elaborate discussion, but I think it's just cleaner to just plug it in and see what it gives us. Right? So what he, because in this case we can solve it exactly. What Weinberg tries to explain to you is how you can see that for the most part, near the origin, this capital R must go like a power law in the radial coordinate little r. You can just plug it in and see that it will work. But let me just skip ahead and tell you how to do it exactly. Right. So first you define a variable called rho. Rho is what? Is square root of 2me E bar times little r. So it's basically, rho is basically r, but in a dimensionless form, right? So M and E are both energy